Hey guys. Sorry, this is a very awkward room. Hey guys over there. So I'll not see you for the rest of my presentation because I'll probably fall down. So welcome, thank you for taking the time. I know we are standing between you and beer. So we'll try to make this quick. This is about architecting a data lake with a bunch of different AWS services. My name is Abhishek. I'm a senior product manager on Amazon Athena. I've been with AWS for about 5+ years now. We also have the honor of having Rohan, who is from Atlassian, and Rohan's going to talk about how Atlassian built their data lake all the way from Sydney. So that's what, 26 hours of flight. Yeah. So the way this presentation is work is, what we'll try and do is try and land this term, data lake, right? So if you've been in the data industry for a while, we'll try and see what does this really mean and why are we talking about data lakes right now. So I'll try and land the term, and the way I'll try and do it is I'll try and tell you why we think when we talk to a lot of customers, they're talking about data lakes. I'll try and put together basic components of the data lake, and then we will show you a couple of examples. And these examples will grow in order of complexity. The first one is a really simple one that unifies real-time and batch data. This is something that we've also put on a blog with a CloudFormation template. So after you kind of run through this, you can go to the blog, click the CloudFormation template, and it'll deploy the infrastructure required to build the data lake. And then we'll go on to a more complex, full-fledged data lake that Atlassian has, and we will kind of peer into their architecture. So if you're thinking of sleeping through the presentation, right now is the best time because it grows in complexity right now. So what are reasons people are talking about data lake? I think there's no doubt that there is an exponential growth in data that is happening. So what we're seeing customers tell us is that they must capture data from different diverse data sources, and they want to break down traditional silos between relational or old databases and new technologies, SAP and social data, or real-time feed coming from a B2C channel and your traditional data warehouses, so on and so forth. So I think this is nothing new. This has been happening for a while. But I think what has happened and what has changed in the recent time, that there is a diversified set of customers for your data. Earlier, it used to be an analyst which would write SQL, produce reports, and the reports would go to a wide variety of people that will look at the reports and make decisions based upon at what level in the organization they have. Now, there are a lot more people. There are people who want to access this data via an API. They want to run a wide variety of tools. There are developers who want to run machine learning algorithms on this API. You want to do things like build models on this API. There's also data scientists that want to explore this data and find correlations that can be helpful to the business. And these are not traditional analysts, so the tools that they use are also quite different from the tools traditional analysts have used. So this is creating a completely new way of looking at data. So people are also asking us for different ways of accessing this data. So it used to be a BI tool or a SQL engine that was good enough for you to capture the data. Now it seems like we need that in an organization, and if you especially have a large organization, on one side of the spectrum you have developers who love nothing but an API, and on the other side of the spectrum you have a business analysts who couldn't be bothered with even writing SQL. So, and there's a wide variety of these people trying to access the same data. The commonality is that they do want to access data at every granularity is possible. So you will, like if you are a data warehouse admin, you will constantly get requests that the granularity that you're aggregating the data right now is not good enough for me. Give me the rawest data format so that I can join and do something else on it. Or you will find people who will tell you that I run a Jupyter notebook and I want to access the raw data, or I run R, and I have a wide variety of tools. Then there are also applications that are built into automation platforms that want to access this data via an API. There's also a lot of customers who are trying to expose this data to external customers and allowing them to run queries on this data, which is also a completely new way of exposing data. So I think this is what is kind of causing us to think about this data lake and to kind of break down silos. That doesn't mean the old traditional way of take your data, ETL it, put it into a data warehouse, and put a BI tool on top of it doesn't work. It works fundamentally fine. Right. So if I think about characteristics of a data lake, these are the things that I think about. That you need to have an ability to collect everything. You need to have an ability to dive in anywhere. That means at any granularity. You need to have flexible access mechanisms, BI tools, Spark, ML algorithms, R, all different types, raw access, API access. And you need to future-proof it, right? So about 2 years or 5, 6 years ago, all machine learning we were doing through was all SAS. Then you have R, then you have Spark, now you have MXNet, TensorFlow. And these technologies are going to keep changing. And they're going to keep coming with new and new ways of better improving these models. So you need to build a data lake in a way that it is future-proof and allows you to incorporate newer ways of accessing the data. We think S3 is a good place. It is one of the places that you can build a data lake. I don't think any engineer will tell you there is only one way of doing something. We think S3 is one of the ways of doing the data lake. The reason we do that is when we talk to our customers who all want to build a data lake, one thing they all agree on is that S3 can be a great place for putting the data. They disagree on how they want to ingest the data. They disagree on how they want to access the data. Some might prefer a Redshift-like tool, some prefer Athena, some prefer to run clusters, Hadoop clusters on top of EMR, some prefer to run instances on top of this. So there are all variety of things, and there is no commonality. But the only commonality we see is they all want to be able to use S3 as a data lake. So what I'm talking about is how to use S3 as a data lake. All of this starts with a very simple architecture. So I think at the end of this presentation, not only will you be a master in data lake, but also in AWS icons. So remember that. But if you think about it, there are 3 buckets of what you need to build. You need to build an ingestion mechanism. You have a staging area or a lake where you can put data. Let's say that's S3. You need to have processing mechanism, and you need to have an ability to consume the data. There are lots of ingestion tools like Kinesis, Direct Connect, Snowball, database migration tools. There are third-party tools that will allow you to ingest data at different velocities and in different formats from different sources in a way that they can all land into S3. There are different ways of processing this data set: Athena, Redshift, Elasticsearch, machine learning services. And then there are a wide variety of ways to access this data. Like you can take something like QuickSight, you can take something like analytic notebooks, also an API. Stick an API on top of this, expose it to an external world. You have people building applications on this data. All right, but there are also a couple of other things that go and become a part of this architecture if you think about it. That's because data is not perfect. All of us, well, let me say data is never perfect. So you need ETL almost at any place. This could be a really small thing as you change the timestamp in a way that somebody is giving you data to a timestamp in which, let's say, a downstream query engine understands it. So there's lots of different tools on AWS that allow you to ETL the data. Some of them are serverless, some of them are full-fledged ways. Lambda will give you trigger-based code execution platform so that you can ETL your data. You can also use AWS Glue, which is an event-based serverless engine. You can run PySpark on top of it. You can also run Spark and Hive on top of EMR. But all of these are doing very, very similar things. They're trying to clean, transform, concatenate, convert into better formats. They are doing transformations on this data, sometimes even event-driven transformations on this data. But essentially what all these technologies do is they allow you to express these transformations as code, right? And Lambda Express allows you to do that. Spark allows you to do that. Glue allows you to do that. So you can express those transformations through code. And this can actually be littered all across your engine, or all across your architecture. It can be right at the time when you're ingesting the data so that you put it in the right format in S3. It could be at a time when you have ETL the data, but you're now pushing this data into a format that it becomes consumable, right? So there's one thing that also we feel is common to all of these is the metadata, right? So I have all these different tools that I am allowing, that are ingestion tools that write data to S3. I have all these downstream query tools that read data from S3. But what I also need is a common metadata store. So we released something called the AWS Glue Data Catalog, which is a common metadata store that allows you to catalog the data that you have in S3 and other JDBC sources like RDS and Redshift. So So it becomes your common metadata store that allows you to search, get connection information, do classification of data, add business annotations to data, add versioning to data. It doesn't have any data, it just has metadata. But it allows all the downstream engines to have a central place where they understand what is this data in S3, and that allows you to use any of the engines replaceably. We also introduced something called crawlers. So crawlers is a way for you to automatically catalog your data that is sitting in S3. We have built techniques that allow us to understand the schema of the data and automatically ingest tables in the catalog. It's very simple. It's based on something called classifiers, which are basically graph patterns that are run in an ordered fashion. And based upon what we think this data set is, we create a table on the data set. Here is how it looks like. So if you can see on the column that I marked, there's CSV data, data from Redshift, data from an RDS data source, data in Parquet. So the catalog is what it is, the catalog of all your data that is sitting in S3. So for example, here you can look at table properties, you can add business annotations, you can add data statistics to the table properties. We also can find things like a new version of the schema in the metadata catalog. And what you can do with a downstream engine like Redshift or Spark or Athena depends upon how your data is actually structured. So some of this as to, is this a new version of the table? Can I actually handle this mutation? Will actually depend upon the downstream query engine that you use. For example, Redshift handles mutations really well. Athena doesn't handle mutations so well right now. So there are ways in which one tool will be good at one thing and the other tool will not be good at that thing. But you can decide. But all of them can share the same metadata catalog, the same permissioning model, and the same annotations, for example. So here's a version control. For example, this gave me a newer version of the table, and it gives me how schemas can be evolved. We also do things like automatic partition detection. Partitioning helps downstream engines reduce the amount of data that they're querying, and thus making the query slightly faster. So go back to our diagram. So we added a new icon to the diagram. It's a metadata store. So if you think about it, a variety of ingestion tools that allow you to write data, a variety of tools to query data, but probably a single S3 data store and a single catalog. So if you think about, then there's also a need for doing real-time processing. And if you wanted to do real-time processing, there are tools there as well. For example, Kinesis. I mean, I don't like the term real-time. That's why I put the word in-stream, because you're actually processing the data in-stream instead of actually processing the data once it's stored on some kind of a data store. So something like Spark Streaming or Flink on EMR or Kinesis Analytics can actually run SQL queries on a stream of data and give you real-time results of the data set. Right? So now if you think about all of this, the only commonality that we see in all of this is here's S3. S3 is a great place to store your data, and here's a metadata catalog. Everything else is replaceable by one engine or the other based upon your use case. So if you think about your data, our data lake strategy, our data lake strategy says, depending upon the way you are ingesting your data, use the source you want to. Depending upon the tool that you want to use it at query, use the tool that you want to. But I think these two will unify your data architecture, the S3-based data lake and a data catalog. So if I go back to, if you think about the data lake, and if you think about any of those things that I just said, they kind of all match within what we set out to build in data lake. Now let's take examples, and we'll do two examples here. We will run through an architecture. Let's say I am an IoT device provider. I have thermostats, and I want to send real-time thermostat information to the cloud, and I want to get real-time inefficiencies of thermostats. I also want to get information about the daily temperatures or averages. So I need real-time data, I need daily aggregations, I need hourly aggregations. How would I build a data lake on that? So that's our first example. And the second one is a much bigger one, which is what Rohan is going to talk about from an Atlassian's point of view. All right, so here's our first example of what we're trying to do with this example is land this concept of a data lake using some of the AWS pieces. So I have some sensors, and they produce record level data. Now, what do I want to do with this? So I have a lot of business questions that I want to answer that I want to ask this data. So like, what is going on with a specific sensor? So that's real-time, that's granularity at a record level. I want daily aggregation that tell me all the device inefficiencies that are there. Tell me the average temperatures across a device across a particular region. Or give me a real-time view of how many sensors are really failing. These are probably the right questions to ask if you were an IoT company. So these are only the business questions. Now the operational question is how I'm going to scale this from 1 million sensors to tomorrow if I go and become really popular, 1 billion sensors. How do I manage high availability? How do I manage less management overhead and only pay for what I need? So what we'll take the concepts that we've just talked about and build an architecture around this. All right, so I have this data. What I can do is push this into something like a fire hose, and that data can land directly into S3. There can be some buffering of the data that allows me to create bigger files, and then I can easily query them on Athena. So immediately I have raw access to the data that I need. So the way to do it would be create a delivery stream on Kinesis. You call whatever you want to call the delivery stream. You denote it with an S3 prefix. Here's where I want the data to be loaded, and there's some other configuration items. For example, if you wanted to do transformation on the data, you can hook up a Lambda function to it. Let's say you don't like the way the timestamp comes out of the sensor data, you can change that. There's also some interesting advanced things that you can do with Kinesis stream, like you can back it up to a different stream. You can also buffer this data for I think 128 megabytes, if not wrong, and then it gets pushed onto S3. So once you have pushed this into S3, you can either use a crawler that will automatically crawl the schema of this data, because this data is in raw JSON, and I can crawl JSON, I can figure out the schema, and then you can write, or you can also directly write a DDL statement, a create table statement that will create a table, and that's it. You can start querying the data, the raw data, as it arrives from Kinesis Firehose onto S3 in its rawest format. So now I have data in S3. I have Athena creating a table. I can run these queries. That's great. Now, so if I wanted to say, tell me all the information about this particular sensor across a period of time, that could be a simple query on this raw data set. Now my second question was, I want daily aggregations. Now I can take this raw data set and I can add a glue-based event pipeline that allows me to ETL this data and create an hourly aggregate of this data and put it in as a new different table on S3. So if you look at my diagram, I have tables. It doesn't have a pointer. I have tables. The raw time series is my raw data. When I aggregate the data, it becomes a daily average table. That's a completely different S3 prefix. And I can query the data as well in Athena. It's just a different table, right? If you take out a glue job is a very simple way of doing this. You take this data set, you aggregate it, you run a SQL query, and now you can run this every hour. There is no servers to manage, and it's simple PySpark script. So I've done this, now I can done this, cool icon, right? Last minute addition, only thing I could find. So what I can do is run this on a schedule. That means run it every hour so that my daily aggregations are here in an hour. Partition it also based upon a daily average. Now I automatically have a daily aggregation of this data. Now if I wanted to do the real-time stuff, what I could do is hook Kinesis Firehose to something like Kinesis Analytics, and there Kinesis Firehose can give, the analytics can give me a daily inefficiency count and push this into S3. So now I have a table that gives me a real-time view of what the daily efficiency was. I can also build a dashboard on top of this. Now, so for example, if I wanted to go to my raw table and get events by device ID, I can get, so I have 3 different tables now, a raw table, a daily aggregation table, and a real-time table. So when I query the raw table, I can get information like this. Give me the events by device ID, give me the top 20 devices. When I query the daily aggregation, I can say, give me a KPI, like give me a daily overall efficiency of the device. Or I can go to the result table and I can run a simple query like top 10 most inefficient devices that I'm seeing on a per second or a per hour basis. This is what the whole architecture looks like. One of the things that you might have noticed about this architecture, that it can scale from hundreds to thousands. It has virtually infinite storage scalability. It has real-time and batch processing layer because we had a real-time table, a batch table, a raw table. We have interactive queries that can run on this table, and you only pay for what you need. And all of this can be done without actually managing a single server across this infrastructure. Now, if you wanted to do this today, you could do this today. If you go to the AWS Big Data blog and search for Unite Real and Batch Time Analytics, there's a CloudFormation script that will take this raw data that has a data generator, like the IoT sensor data that simulates it, and has a CloudFormation template that will set this entire architecture up for you, including the crawling, including this. So from 0 to nothing, you have built an architecture that not only allows you to do batch, it also allows you to do real time, and allows you to build this on this, allows you to build it on S3. So that's probably a very simple example of how you would want to build a data lake. Now, to talk about a lot more complex example and a lot more enterprise use case, let me invite Rohan.
Thanks, Abhishek. Hi, everyone. So I'm Rohan Depelia. I'm the Analytics Platform Manager of Atlassian. And I've been with the company for about 3 years now. And I manage a team there of awesome data engineers and full stack developers. And together we've driven some awesome changes to Atlassian's data landscape. So today I'll be talking about Atlassian's data lake, how we handle some of the core components of the lake, and drive a self-serve, zero-friction approach to managing the lake, as well as some of the challenges we've faced along the way. I'll start with a bit of an introduction into what Atlassian is. I don't know if everyone here is aware of what Atlassian is, but we make software that helps teams of all sizes organize, discuss, and complete their work by providing a shared, open platform and tools that take advantage of that platform. Tools like Jira software for project issue and planning, Stride, our newest product, a team messaging and communications tool, Trello, which helps individuals and teams organize and prioritize their work, as well as Confluence and Bitbucket. Our data lake is pretty young. It's only going on 2 years, and that's been very much to our advantage. We've been able to really learn from others in the industry and make some good decisions up front. Even though it's so young, it's been widely adopted in the company, and it's become pretty much the single source of analytics for Atlassian. We call our data lake Socrates, and the name stuck pretty well so far. It's named in reference to the Socratic method, a means of cooperative argumentative dialogue between individuals based on asking and answering questions to stimulate critical thinking. And we kind of hope that our platform allows our users to do the same thing, essentially ask more and more questions to get down to the real deep answers. To give you an idea of scale, we have plus of 500 terabytes of data in binary compressed format available for access on S3. We ingest over 1 billion events every day. We have around 100 integrations into the lake, and we have 1,000 weekly active users of about 2,000 plus, somewhere around 2,000 employees at Atlassian. So it's mostly internal analysts and whatnot. The data lake is managed by the analytics platform team, a subset of the data engineering team, and we're about 9 developers. And we split our focus across these 4 pillars here, I've highlighted in blue. There's ingest, which is how can we get data into the data lake in a low friction, low maintenance way. There's prepare, which is like, how do we really add value to the data by modeling it, aggregating it, and deriving information out of it. There's organize, which is how can we ensure data is secure, but also structured to scale. And lastly, there's discover, which is like, how can we enable our users to find, understand, and visualize data without having to ask a data engineer for assistance? So in the following slides, I'll talk about how AWS's offerings have helped us move up the value chain in each of these pillars and allowed us to focus on providing greater value to our customers elsewhere. Starting with ingest. So we consider this to be one of the key pillars of the data lake. Our goal here is to make the management as low friction as possible. the less time that, I believe, the less time that my team and other Atlassian teams can spend focused on getting data into the lake, the more time we can spend focusing on adding value elsewhere. So some of the challenges we've had up to now, I guess, to give you an idea, like up until now, we've always been doing like pool-based ingestion. So the challenges I'm speaking about here are mostly centered around that. When we started our data lake, we were aiming for a quick minimum viable product, and we really wanted to prove value fast. So we decided to go to each individual system and extract data by whatever means is necessary. But this led to a few problems. We had very brittle pipelines in that sourcing systems would change, either the data model or the API, or they would have downtime when we're trying to extract. And this was quite problematic for us. There was complex interfaces in that, like, my team had to understand various technologies, like various sourcing system technologies and how to actually connect to those sourcing systems. And it was just made it harder for me to hire people and harder for us to train up newbies as well. And lastly, the pipelines were disruptive on sourcing system teams. So, like, you know, our pool-based extracts would be like a performance hit for them. And like, it will cause all sorts of failures and downtime on their side as well. These problems combined started to discourage potential data producers from actually contributing to our data lake and caused a high barrier of entry, as often they would have to wait for our team to help them get the data onto the platform as opposed to being able to self-serve and do it themselves. So a quick glimpse into our ingestion journey up until now. When we started our data lake, we were only pulling data from our web assets, our billing and CRM systems, and our products. And this essentially provided us, or provided analysts with visibility from the moment there was a click on a website to when a product was purchased, and through to like analytics around the behavior of our users in product as well. And this like really just helped generate some people actually using the data lake to begin with. We then started to, like, by early 2016, we saw an explosion of microservices released across Atlassian. And Socrates was also proving to be a very successful platform within the company, with more people wanting to take advantage of its offerings. We continued to help teams onboard their data, but whatever means necessary. And we tried to accommodate for any means of integration, really. But this led to a multitude of interfacing technologies. Started to lead to like a series of problems, and it really took a toll on the team. We began to see reliability issues with numerous extracts failing daily, and like probably 20 or 30% of them would fail every day. So later in 2016, another Atlassian team released a platform called StreamHub, which was an enterprise bus. This awesome little cylinder here. And producers could essentially send data to a single endpoint, and consumers could subscribe to events without having to worry about the complications of sourcing systems. So we started to see our sourcing systems had already started to push events to StreamHub, and microservices and enterprise systems had started to subscribe to those events as well. So we saw this as a good opportunity for us to subscribe as well and take advantage of this vast amount of data that was available there. So what is StreamHub? Essentially, it's an event-driven architecture, which means essentially different producers could integrate with the platform in different ways, and downstream systems wouldn't even know how or care. And secondly, it has a schema registration, which means messages sent to StreamHub were pre-validated to a contract, and we had a schema available telling us how to read and materialize those events in our data lake. I'll just walk into like how it's kind of architected, StreamHub specifically. So its implementation is mostly on a microservice architecture built on EC2. The journey for a publisher starts with the Schema Service down the bottom, whereby a publisher can register a JSON schema for the event they intend to send to the service. And schema registration, like it's quite self-service. Basically, they just submit a pull request to the service and upload their schema. The API is the gateway for publishers to submit events. And it's at this stage that we also authenticate the publisher, and we validate the event against the Schema Service. Once the publisher's events have been validated and authenticated, they're sent through to a Kinesis stream, And then there are two things that kind of happen here. One is a subscriber would register their intent to consume that message. They would do this by creating a regular expression predicate and submitting it to the Schema Service. And then the second thing that would happen would be a demuxing service would take these events off the Kinesis stream and decide which subscriber needs those events based on the regex predicate, and then fire it off essentially to whichever subscriber it is. At the moment, it currently supports SQS and Kinesis as consumers. So the StreamHub service maintains a contract with its publishers and subscribers. They try and maintain a 99.95% uptime SLA, which is less than 21.5 minutes downtime per month. 99.95% success rate, so 1 in every 2,000 calls fail. And a 500 millisecond latency between when the event arrives at the API to when it's actually sent to the consumer. And they also offer at least once guarantee here. So then, how do we land this data in Socrates, our data lake? It wasn't as easy as setting up a fire hose and landing the events. What a fire hose would do, I guess, would consume one stream of events and land those events in one location in our data lake. But what we wanted to do was consume one stream of events of multiple event types from multiple publishers and land those events as multiple tables in our data lake. So varying tables based on like the sourcing system and the event type. On top of this, we wanted to ensure that we could do things like mask PII for any events that are coming through on the pipe, and that we could land the data in a format that's easy to consume, that's Parquet formatted, snappy compressed, and not just JSON strings, like so a columnar format, essentially. So we built a data landing framework. And what this framework does is essentially it takes events off the Kinesis stream using a Lambda and lands these events in S3 as raw JSON. The files in S3 are stored as compressed JSON in paths that are based on the event type and the date of the event. And it's now, we could start exposing these events in our data lake in Socrates, but they would be very difficult for our users to consume still, as they still are in JSON. And they're not stored in a columnar format that would work best with our query engines. So the next phase of processing takes these landed events, and using Spark structured streaming, we re-land these events in Parquet format and snappy compressed. We use the schema enricher service to basically read the JSON schema that we get from StreamHub and determine the structure of the Parquet files as well. And we also allow for things like enrichments here, so you can mask particular fields if you want to, or you can do custom partitioning or whatever you need to do there as well. And it's at this stage as well that we also expose the data to it in our data lake. So now that it's in Parquet format, we can expose it in our data lake. Essentially, it starts to look a bit like this now. So you have the data in Parquet format. And you can see that we also have custom partitions here too. So while the events at this stage would be consumable, they still wouldn't be performant enough. We still have the problem of having thousands of small files in every partition. And this will be problematic still for our analytical engines. Like the Spark, the data optimizer Spark job runs every 5 minutes. So you're just going to get like a new file every 5 minutes essentially. So what we've done is we've created one last step. There you go. It's basically a daily compaction job. And all it does is it takes the small files in each partition and concatenates them together. And then on top of that, we'll just basically alter the partition. So from the unconcatenated path to like the new path that we created with now the concatenated data. And this starts to look just like this, like basically one file in every path, every partition, as opposed to having many thousands of files. So this is the entire landing framework so far. In the future, there's a few things we would like to do. For one, we would like to remove the landing bucket that we have here and have the data optimizer step read straight from the Kinesis. The second thing we'd like to do, ideally, is eventually just replace this data optimizer step entirely, if and when we get things like Parquet reading, probably from Firehose or something like that, and just get rid of it all entirely. At this stage, we can't really do that, though. So moving on, prepare. So we talked about the importance of ingest and how to reduce friction there. But still, the true value really comes once you can aggregate or derive more meaning out of data that's been landed in the lake. So without providing an easier service in this area, like we're basically forcing our data analysts and our data scientists to learn complex big data technologies. And that's not really what we're here to do. So in this section, I'll walk through some of the challenges we've faced and how we've tackled each of those challenges. So in the 2 years we've been running our data lake, the following challenges have become quite apparent. One is that there is a data engineering bottleneck, by which I mean data analysts and data scientists and other data consumers are typically heavily reliant on data engineering, and they need help to do things like create tables, scheduling them, or knowing how they run. The second thing is cluster management is an issue for us. Particularly you have a cluster running multiple jobs on it, and if you want to, it's very difficult to attribute costs back to clusters, back to jobs I mean. And it's also quite problematic to try and upgrade clusters. So if you have a cluster with 100 jobs running on it, and you want to upgrade it, but 10% of those jobs fail, you'll be in a state where you have to kind of run two clusters side by side for a period of time, and that's quite expensive. And lastly, reinventing the wheel, by which I mean data engineers spend a lot of time solving solved problems. Things like, how do I land data in S3? How do I do incremental loads of data? And how do I do incremental loads of data where I want to reload a few days of data every day? Like I can't really do updates. And what I see is that data engineers can solve these problems, but like across the data engineering teams at Atlassian, everyone has a different way of solving these problems, and there's no similarity. There's no like same ways of doing these things. So what we provide in the data lake is raw and unaltered data, but the true value comes from the prepared and transformed data. Things like dimensional models, whereby we can properly report on business processes against conformed dimensions and attributes. Aggregated and derived views that we can use to push onto reporting tools like Tableau or just make it easier for users to query and understand data. And user-defined extracts that our users will use for machine learning models or for a particular notebook or some analysis that they're working on. So given the cluster management challenges I talked about earlier, we've moved to a model of having job scope clusters. This means that we dedicate one short living cluster for every job. And we shut it down essentially after the job is complete. So spin it up, run your job, shut it down. And we use Airbnb's open sourced Airflow to manage the spin up and shut down of that. So there are many benefits to job scope clusters, but I'll just list a few of them. For one, you can actually now understand the cost per entity and job, and take advantage of things like per second billing in EMR. And you can also charge back to your customers if you wanted to, like your analysts. Like you can say you're using $20 worth of compute every month or whatever. You can upscale clusters for particular jobs that are more resource intensive. And you can take advantage of later versions of EMR, Spark, Hive faster by just upgrading everything and keeping problematic ones like quarantined on an older version of EMR. So this is an example of a typical DAG, a directed acyclic graph that we have in Airflow. And the beauty of DAGs is they give you predefined steps, and you can build predefined steps and standard actions that we can use across all DAGs. And so this kind of helps us stop from reinventing the wheel. We can reuse things across all our DAGs and across our whole data engineering org. In this DAG, we're doing a few things. So we're basically spinning up a cluster, running a particular transformation, and then copying the logs across for debugging to S3 in case anything happens, and then shutting down that cluster afterwards. So we kind of solved job scoped EMR clusters. We can avoid reinventing the wheel by using things like DAGs with predefined steps, but we haven't really solved the data engineering bottleneck yet. Users still need help creating aggregated and derived views. And to solve this, we created TAS, Transformation as a Service. And I guess this is us trying to move up the value chain a little bit in my team. So this allows our users to self-serve, and it's almost pretty much zero friction with our team at this stage. And all it is just a UI where you can basically submit a Spark SQL statement. And in the future, we're looking to do something like add a CLI as well, whereby you can then use it in a build plan or like a continuous deployment sort of thing. Like I said, it accepts Spark SQL. You can do things like date parameters for incremental loads as well. And users can run ad hoc, kind of like a create table as select statement, or they can do things like schedule their transformations at varying frequencies, be it daily, weekly, monthly, or whatever. Behind the scenes, we're still doing the same things. So we're still creating DAGs and ephemeral clusters. And so far, service has been pretty good. In the 3 months since we've launched it, we have around 75 scheduled transformations. So moving on, this is the third pillar, organize. So how do we structure and secure our data? How do we ensure the right people have the right access? Like, this was pretty easy to do in like an RDBMS world, but it's proving to be a lot harder in a big data world. And how do we enable self-service and provision areas for people to work freely? The challenges we have with organizing are, one, teams want flexibility. They want to structure their work in a way that's meaningful to them, and they don't want us to dictate how entities are named or how they should structure their spaces. Security, how can we ensure that our data is secure on land and still enable our users and their team members to access what they need to do easily? And lastly, categorizing data. How do we structure our data lake so it will scale? So I'll start with categorizing. In our data lake, we essentially have four areas. We have the landed, which is not exposed to our users, not performant for query engines, but we keep it around just in case we need to replay any ETL. We have raw, which is partitioned and optimized data, usually columnar formatted. We mask any sensitive data here, and we expose in our data lake at this stage as well. And we have models, which is certified and conformed entities, typically entities that have been built and maintained by the data engineering team, and are usually entities that contain like critical business metrics or core referential data that is used by many users across the company. And lastly, we have self-service, which is like a space where teams can build their own entities, upload their own data, or perform a transformation on some of the raw data that we've provided. So I'll talk about how we kind of promote self-service. So we use our Jira Service Desk, a little plug there, and basically you can request a new schema. And we do act a bit as a gatekeeper here, and we don't want to have too many schemas in our data lake, but what we do is like try and limit them to be like at a team level or at an organization, a departmental level at most. When a user requests a self-service schema, a few things happen. One is we provision a S3 bucket for them. We tag it to the user, and we tag it to their business unit as well, so we can charge it back. We create a schema in our meta stores, and we create an Active Directory group whereby they can maintain control and access to their buckets themselves. We call these schemas zones. We used to call them playgrounds in the past, but we found that people started to use them quite a lot for production loads, so zones was a bit more of a generic word that we could use for anything. And we use Vault to control access rights. And Vault is essentially an open source tool. It's designed to manage secrets. It creates a temporary IAM user with like a 2-hour lifespan and passes those credentials onto the user. So this is pretty much how it works. So a user would sign in with their LDAP authentication. They pick the policy that they want to use. So in this example, we have like a zone marketing write and a zone marketing read. And then they can read those credentials for that policy. They can then use it for whatever they want, really. So in this example, they're basically listing an S3 bucket and then uploading files to that S3 bucket. So this is, I think that's it for that one. Oh wait, did I miss a slide? No, yep. Okay, so that's pretty much it for that pillar. Moving on, this is Discover. This is probably the most neglected pillar in our data lake so far. Up until recent months, we believed that the other three pillars were of higher criticality and more important. Before we could really have a look at this. Here we try to enable our users to find what they need, to understand it, and to be able to deep dive and find insights without having to interact with the data engineering team. The core challenges we have here are that teams want options. We can't just offer one visualization tool and say we're done. Different tools have different pros and cons, and we need to provide as much flexibility as we can here. Secondly, managing query engines is time-consuming. Query engines are the main way that analysts interact with the platform, but they also take a lot of time to get running right. And lastly, finding data is hard. We have over 3,000 tables in Socrates, and it's difficult for like a newbie or like a well-seasoned analyst to find data in the lake. So this is kind of all our data is stored in S3. This is that's our storage area. And the beauty of that is that we can spin up any type of compute that we want to access it. So this gives us flexibility and tools that we choose. So for example, if Tableau doesn't really work very well with Presto on EMR, we can easily switch it out for something like Spark or Hive on EMR as well. And it also, another thing, it gives us flexibility to make significant changes. So at the beginning of this year, we decided to stop using Presto and move to Athena. I'll go into the reasons for why I've done this a bit later on. But the point here is that the change was really simple to do. We didn't have to migrate data anywhere around. It's all based in S3, so it's just a matter of pointing, getting the metadata up into Athena to make it work. In recent months, we've also looked at dropping our self-managed IDS Hive metastore in favor of the Glue metastore. And this is just basically a way that we're trying to simplify our architecture as much as we can. So before we had Presto, we had several issues, mostly due to our own poor management of the cluster. We would rather spend our time doing other things rather than managing a Presto cluster. So we had queries failing all over the place. And on top of this, we had a hard time of enabling table level security. There was some work being done by the open source community to enable this, but we were having a hard time implementing this in our ecosystem. So we implemented Athena, which gave us the ability to attribute cost to our users, less infrastructure to manage, so the team could spend more time doing more value add stuff. And we don't have to pay for what we don't use. So if there's no queries running on the weekend, we don't have to pay for it. And also it uses S3 level bucket security policies. So we don't need to worry about enabling authorization at the query engine layer. But there are challenges with Athena. We were an early adopter. So we started migrating to Athena as soon as it went GA. And we hit a number of hurdles and teething issues in the service along the way. For one thing, there wasn't parity with Presto. They were both running on the same tech, but there were still some functions and some features that weren't working in Presto that weren't working in Athena that work in Presto. So we had to keep both clusters up and running, or we had to keep Presto up and running for a period of time while we had Athena up. Secondly, there's no AD authentication, and by which I mean there's IAM users and roles to authenticate with, but this is not really, this will work for lots of companies. It didn't really work for us. We would much prefer to have our own AD authentication in front of Athena. So what we have built here is a proxy in front of Athena that just basically accepts AD authentication and converts it to an IAM user on the other side. And lastly, cost management. In the time since we've been using Athena, we've been hit a few times by this, whereby we haven't really been paying attention for a while, and then the end of the month comes and we get this surprisingly large bill. And it's usually just because a user's been querying it and it's been too high a frequency, and like there's a bit of monitoring lacking at the moment. I'm sure it will improve in time, but at the moment it's a bit lacking. However, overall, at the moment we feel like the benefits outweigh the costs and the challenges, and Athena is likely to improve and probably surpass anything that we can do with Presto. So we provide a number of visualization tools as well. The 4 that we provide are primarily Tableau, which we use for exploration on core data sets and corporate dashboards. Shiny are used for web apps and mostly for and for very niche requirements. Zeppelin notebooks, which is like we run in EMR. It's a web-based notebooks, usually for quick analysis in Python and Spark. And lastly, Redash. This has been one of our probably most successful ones, in that it feels very similar to like a client database visualization exploration tool. In that you can just run any kind of query you want, get the results quickly, get a visualization up, and schedule it to run whenever you want. It's quite cool. But like, just because we offer these 4 tools doesn't mean we don't stop for people from bringing their own. Like, we want to provide as much flexibility as we can. We just manage these at the moment. And lastly, in an effort to kind of solve the whole data discovery problem, we've built a search functionality on top of our data portal. It's still a work in progress, but the idea here is that where we want to get to is like a community of analysts and data scientists will contribute to this data catalog, and to make it easier for others in the community to find data better and understand data better without having to reach out to us. So that's pretty much it. In the future, key takeaways that I hope I've kind of shared amongst this is one is that AWS helps you move up the value chain. They provide services for things that are becoming commodity and utility. For example, Kinesis versus running your own Kafka cluster, or Athena versus running your own EMR Presto cluster. And this has helped us spend less time maintaining things and more time focusing on adding value elsewhere. And secondly, it's not all that easy. You can't just spin up a Kinesis stream, a Firehose, and have an instant data lake. You often have to build services around these things to make them work for you. And like, I guess that's when you have to start thinking about like, how can you make these things scale, and how can you add flexibility? So that's it. Thank you. I hope there were some takeaways in this for you. If you're interested in finding out more about what we're doing, you can reach out to me afterwards. We can have a chat now, and otherwise you can catch me on LinkedIn. Thanks. And thanks to Abhishek.
We can take questions if you guys have any.
I have a question. How big is your team?
9 developers in the analytics platform team.
9 software developers?
It's like a mixture at the moment. So we have we have data engineers, but we're also most recently been hiring full stack developers to kind of build like UIs and some of the applications around.
How long did it take to do software design resources?
Like I said, like 2 years. So we started off, about 2 years ago, pretty much to the day. Go, sorry. Yeah, we did. We still do. We still have some clusters that do run with Yarn. But the beauty of EMR and job scope clusters is mostly the chargeback. That's like what I'm most interested in. So like being able to charge back those costs to our departments and things like that.
What I specifically meant was like maybe instead of using like fair scheduling, using like food scheduling or different other like scheduling operations for Yarn, so that you can kind of get to the same benefits that you like and you have a translate cluster.
Yeah, we do a bit of both. So sometimes we use Yarn, sometimes we use JobScope. Yeah.
I noticed like your billing system seems to be a relational database, right? How did you extract
So in the past, we were mostly doing like extracts via JDBC. So we'll hit their RDBMS databases and extract. We're moving more towards event-driven. So yeah, so whereby they would fire an event whenever something happens in their system.
Already established model and contracts using your Cisco or MuleSoft, rather than repointing those contracts to the Amazon Service Bus, would you recommend then taking a MuleSoft-like tool and connecting directly, and then just having that be your enterprise service bus to your extended service, your cloud service bus into your technology in the cloud?
Well, I guess let me think of. So like our aim is to have one pipe in, like one means of ingestion. So like you could have like the idea of using StreamHub, like that enterprise bus, was that it's already well established, and we could have then we just have the one link to worry about, and it's like just less maintenance.
So I'm okay with that. I'm actually looking at the number of contracts going into StreamBus, because you had all these different disparate data sources and systems, right, going to StreamBus. But what if you already have all those disparate systems going into an enterprise service bus, such as Cisco's, or now you only have not just one stream, you have one system talking to StreamBus directly, because you've already taken and abstracted all that from internal.
Yeah.
Okay? You got one
So you're saying if you had like something like MuleSoft already as your enterprise bus, then you would just use that, I guess, and you would just ingest from that, and that'll be your enterprise bus.
MuleSoft to StreamBus.
Yeah, you would probably not do the middle step then, right? You would just have your MuleSoft enterprise bus, and you have some means of ingestion into your data lake from that one thing. Anyone else? Yep.
So you talked about your architecture where data goes through a lot of detailed processes. There's Lambda, there's runs, streaming, and all. How do you manage that so that, let's say an attribute changes and you have to track what all the processes are touching?
Okay, good question. So if an attribute changes, how do we manage that change? So with StreamHub, they do, the schemas are registered, but they're registered against, like they have a versioning in the registry. So if a breaking change happens to that event, they register an entirely new schema with a new version. And what we do is we basically land that as a separate table in Socrates. So the breaking change won't affect the previous event plus version, but it'll like basically build a new table. And then what we're hoping to do in the future is have like views and Athena over the top of that, which kind of combines those multiple schema versions for that one particular event type.
Catalog also does the same thing. You would have to create versions anytime you see any kind of attribute mutation, because otherwise the underlying engine will just be it might just have wrong data. So you'll have to create versions.
Yeah, and also the question was, there's a lot of data transformation logic sitting in Lambda, sitting in streaming, and all these things. And how do you maintain that? Like, how do you know where's all, like one attribute gets transformed by so many processes?
So we try and keep the transformations, like we try and keep the data as raw and untouched in all those places. So like the Lambda is not actually doing anything other than just like splitting the files out. So we're not actually doing anything, we're not actually modifying the context of that file at any stage. It's only in the data optimizer stage that I showed you, that's where the only place we're actually doing any sort of transformation. To keep it like narrowed.
First, thank you for the presentation.
Thanks.
The graphics are amazing. You have a good sense of
Thank you.
yeah.
Yeah.
So question is, have you ever had data that's encrypted coming through, and how did you deal with it?
We are looking at how we're going to do that. At this stage, no, we haven't had any encrypted data yet.
Where are your keys?
Say it again.
Where are your keys for the encrypted to decrypt the data?
The key is.
Is it on KMS? Is it on
you have to
HSM?
provide them with a public key, right? The source. Then you'll have a private key.
Yeah. So with S3, if you can encrypt using either your own encryption or client-side encryption and put the keys in KMS.
Yes.
And then you can have individual users who could have different keys for different prefixes. So if I'm user A and I only have access to data in a certain prefix or a certain, let's say, directory, I only get access to a certain key that can decrypt that data. I don't get access to all the other keys. So that's one way of doing it, that you provide permissioning on the key level itself and change, and as your data classification changes, encrypt them using different keys.
I guess you still have to add the extra step for decrypting get transport. Right?
Generally, you would use something like Spark understands this, Athena understands this, Hive understands this. All these systems have a way in which they can pull out a key and decrypt the data when they're processing an S3. All of them support client-side encryption with keys in KMS.
For your self-service transformation as a service solution that you showed,
Yep.
you said you have 75 jobs.
Yep.
Do you make any attempt to run jobs that are scheduled for the same time on the same cluster, or you keep them just one-to-one?
So we basically set a limit on the cluster that we're running at the moment. We are trying to move to a stage, I guess what happens is they kind of get queued up a little bit. So we're not really, at the moment, they're not entirely job scope clusters at the moment behind TAS. It's mostly one big cluster, and we have multiple jobs, or we're moving towards like job scope clusters, and then it wouldn't really be a problem for us regardless, right? If you have multiple jobs just spinning up, we'll just spin up more and more nodes. Yep.
Could you explain a bit more on why you're using Hive Metastore instead of Glue?
Yeah, so I did kind of explain there a little bit that we are trying to move towards the Glue Metastore. So yeah, we have got both up and running at the moment. We're in the stage of shutting, with all our email clusters. I think Presto is the only one that doesn't actually work with Glue.
Last week it started.
There you go. So now I think we can probably do it for everything.
Yeah. So when we released, it was only Hive and Spark, but last week we released EMR, Presto running on top of EMR with the Hive store. Yep.
Okay, I think we're almost out of time. Yep. Go on, sorry.
You mentioned you had two stages as a Firefox or Kinesis, which
Yeah.
was the optimizing and the compaction.
Mm-hmm.
So two questions related to that. Do you do some sort of auto-scaling for the EMR clusters that will transform the data and compact it, depending on the volume of the Kinesis stream? How do you monitor that? Do you have an adjustment?
Yeah, at the moment with the Kinesis stream, we've just over-provisioned the Kinesis stream, so we haven't got any sort of scaling there. With the cluster as well, we've just over-provisioned, but we will look at probably doing something there too.
Have you considered using Glue jobs for that?
For that part, not so much, no, but we have looked at using Glue for some of the preparation work that we're looking at doing.
So let me answer that because we used to do product on EMR as well. With EMR autoscaling, I think it's probably much easier if you did the scale up based upon your CPU load, which will be a function of, let's say you have a giant feed coming out of Kinesis. So let's say after 1 hour, you see that your CPU load is still sustainably at 70% or 80%, then you can scale out the cluster to get your job done. And with per second billing, you can actually aggressively scale it out. So instead of trying to do it on the Kinesis as to how quickly the stream is coming and monitoring them in CloudWatch and then calling the EMR cluster, you might actually just do it in this. Because what that will also do is it will also help you with skews. Right? If your data is awfully skewed, but it's not that you're getting a higher volume out of Kinesis, but it is awfully skewed, your aggregations will take a longer time. Right? So that can actually help if you just do it on the CPU. Nope. Thank you, guys.